So suppose A is an abelian group and we have another group, say G, any group that acts on A from left side. So we say then A is a G module. So this will imply that A is a G module. So one can easily see this is same thing as saying that A is a ZG module, where ZG is the usual group ring because you take any element of ZG, it should look like some finite combination of integers times elements of the group. And if you have a G action of on A, then certainly you can take this action of ZG on A. This will be again an well-defined action. So this will imply A is a ZG module, and vice versa is obvious because G is inside ZG. And by a G homomorphism, we mean just an abelian group homomorphism is G homomorphism if uh, it's a homomorphism between these two abelian groups, and secondly it should be compatible with the action of G. And the set of all these homomorphisms, that G homomorphisms, will be denoted by hom AB with a G uh, in behind. So this will be the set of G homomorphisms between A and B. So these will be our primary objects of study. So our goal is to construct cohomology groups of abelian group A, and we'll then see some specific relation between a cohomology group of a subgroup of G with the cohomology of G, and we'll see some specific kind of maps in between them, and also how we can construct cup products between two cohomology uh, groups that will make it a cohomology ring, just as we do if you know in algebraic topology. So some things will be similar, but yeah. Uh, to begin with, first have to construct uh, the cohomology groups. So construction. So as we know, to construct any cohomology group, you need a chain complex, and then you can take the kernel mod image, and at each step, at each level, the quotient will be denoted by uh, cohomology of that step. So in general, to compute group cohomology, we'll start with a projective resolution. A projective resolution is denoted by P with a dot up top of these abelian group set as trivial G module. Okay, so what does this mean? It means that you have a sequence or an exact sequence of projective modules. This thing that ends with Z, where each EI is a projective module, projective G module. Okay, and Z itself is a G module if you just act G on Z trivial, and then it's the usual thing. You apply this contravariant functor on it. So it will switch all the arrows, and you drop the first one, that is Hom Z comma A, and then you get a chain complex and you take the usual cohomology. So you denote the ith cohomology of G comma A as the ith cohomology of this chain complex that you will get uh, by this. And you take Hom with respect to all the G homomorphisms, which is expected. Yeah, so this is a chain complex, and you take the cohomology of this thing. So that's a good thing. Also, there are few easy observations to note that may help us later on. That if you take all the G homomorphism between Z comma A, that will just be isomorphic to the G invariant set of A. That is, all the elements of A that are fixed by the action of G. And that is kind of obvious because you take any map from Z to A that is a G morphism and you send it to its value at 1. Yeah, so that is obvious because this element is indeed fixed by the action of G, because this is just this. And again, here we are taking Z with respect to the trivial G action. So this will just be this. And, uh, and this is an isomorphism because if you conversely start with an element X from here, you send it to a map phi that sends 1 to X. Yeah. And if you know the value of 1, you can um, you can determine any other values because the domain is there. So that's something easy. And also the usual properties will hold. Usual properties of any cohomology, that if you have a G homomorphism between A to B, the functorial property, sorry, G homomorphism, then the induced map is from G, sorry, to GB. This is the induced map usually. And secondly, the another thing that is almost there in all the cohomology theories, that short exact sequences of G module gives rise to long exact sequence of cohomology. That is again there in topology and everything. So it says that if you have a short exact sequence, this is a short exact sequence of G module, this will induce a long exact sequence like this. Where these are the connecting maps. Yeah, and I wrote this AGBGCG because if you compute the zeroth cohomology group, it will exactly turn out to be this. And that can also be seen from this observation because this is precisely the zeroth cohomology group of G comma I. Yeah. And to prove this, you need the standard application of snake lemma. Yeah. So let's see some specific projective resolutions, because so far I have just constructed, or I have just said how to construct cohomology groups without referring to any specific projective resolutions. Let's see some standard projective resolutions which have which will be helpful for us later. Some specific resolution. So let's see first one type of resolution. So you consider this ZG bar I plus 1 as ZG module. Okay. Where G bar I plus 1 means just I plus 1 fold product of G. And the action of ZG is obvious because you take this, you have I plus 1. So you run from G naught to Gi and you just act G component wise. This is the action by which this becomes a G module or a ZG module equivalently. And if you define these maps, like you take any element here, you send it to this element, where you just remove the jth part because this is one less, so we have to remove something, and you just add a sign with respect to that, and you add for all j from 0 to 1. Yeah, so you can show that this becomes this delta I maps make this resolution. So this is just, so one can usually show that this is a, this each term is a, in fact this each zg bar I is a free zg module that can also be shown. And so they are in particular projective zg module or a g module, and where the last map is again kind of predictable, you just send g to 1, or in other words you just send this to this. So this becomes a projective resolution, and again you are taking z as trivial G module, and then you just take hom dash comma I functor on this projective resolution and compute its cohomology. So, but one thing to note here that this ith cohomology in this way will be the I plus 1th of hom zg. If I denote this as take this, yeah, and it is clear why we have to take one more, because we are defining these delta is from I plus 1 to I, because when we defined when we said how to construct the cohomology, we take the from pi to pi minus 1, then take the ith cohomology, but here we are starting from I plus 1. So yeah, that's one thing. And there's another standard thing we can do, so that you can do directly without referring to this group ring. How do you do that? You just consider for each I, you consider all the maps from G par I, the I-fold product of G to A, which in short you can denote by this. And there you can define these maps, take any F, send it to this, which is a map from I plus 1 full product of G to A, where you take an element of this, you first you send it to Remember, F is a map from G power I to A. So domain of F should be just I tuple of elements of G. So here we are removing the first one, so we are in good shape. And for the other ones, we just take somewhat similar to the last one. You go till uh, J minus 1, and then you combine J and J plus 1, and you go again similarly up to J, and you take the sign of J, and you run from 1 to I, and the last one is again obvious. You forget the last code. Yeah. So these are two standard things, and again this becomes a chain complex. This C I G comma I, this becomes a chain complex with respect to these del I maps, and computing cohomology just becomes computing the cohomology of this complex. Yeah. So these are two standard things. So, and in particular, when we are talking about cohomology, we are taking kernel mod image. So the elements of the kernel will be called usually ith cocycle, and the elements of the image will be called ith cobound. So in particular, we'll be mostly interested into two cocycles, that is the second cohomology groups. So let's see what an explicit element of second cocycle looks like. So this is just a map from this to this. There is a two cocycle. If you have to go via this definition two, so this will just uh, be, so let's put uh, I to be 2. So this is just a map from this, and the image, that is del I of f, should be 0. So this means that a of, so first you take a g dot this, and you alternatively change the sign. Okay, okay, and lastly you forget the last code. This should be 0, written additively for all element. This is a typical element of 2 cosine. Yeah. So I'll stop here. Next time I will show the relation between group extensions and the second cohomology group. That's where we'll need this the description of the cocycle. So that's why I did it. So next time I will define what's a so next time I will define what's a group extension, and we'll show how the elements of the second cohomology group and the group extensions of G by A are related. So that will be a topic of concern for the next video. So let's stop.